In this segment, we'll talk about how to find coefficients of thermal expansion. We'll take an example. So we are basically interested in calculating the coefficient of thermal expansion alpha 1, which is in the direction of the fibers, coefficient of thermal expansion alpha 2, which is perpendicular to the fibers. These are the formulas given for alpha 1 and alpha 2. What I would like you to observe, although we have derived them in an earlier segment, is that it is not a simple rule of mixtures. It not only depends on the thermal expansion coefficient of the fiber in the matrix and the volume fractions of the fiber in the matrix, but also on the Young's modulus of the fiber in the matrix. And if you look at alpha 2, it has an additional component or variable on which it depends, which is the Poisson's ratio of the fiber and the matrix. So let's go ahead and take an example and find out alpha 1 and alpha 2. So here is an example. We want to find the two coefficients of thermal expansion for a glass epoxy unidirectional lamina with 70% fiber volume fraction. So that means that the volume fraction is 0.7. If we are talking about fractions here, we're given the properties of the fiber, we're given the properties of the matrix. So the volume fraction of the matrix will be 1 minus 0.7, which is 0.3. So those are the numbers which we have to look at. So let's go and see how we can calculate alpha 1 and alpha 2. So if you look at alpha 1 is 1 divided by the Young's modulus in direction 1 times alpha f, EF, VF plus alpha m, EM, VM. So of course we have to calculate the Young's modulus in direction 1. So let's go and do that first. So E1 is nothing but by the rule of mixtures given by this formula right here. So we know that the Young's modulus is 85 gigapascals. Volume fraction is 0.7. The Young's modulus of the matrix is given as 3.4 gigapascals. Volume fraction is 0.3 of the matrix, and that gives us 60.52 gigapascals. That's the value of E1. So let's go ahead and substitute all the numbers which are now available to us. So we have 60.52 as the Young's modulus in direction 1. Let's now substitute these values for these 6 variables. So we will have as follows. This is the thermal expansion coefficient of fiber. EF is 85, VF is 0.7, alpha M is 63, 10 to the power minus 6, meter per degree Celsius, and EM is 3.4 gigapascals, and the volume fraction of the matrix is 0.3. So if we do these calculations, we will get 5.978 times 10 to the power minus 6 meter per degree Celsius. We didn't have to convert the Young's moduli into pascals because it canceled with this one. But it's a good idea to convert everything into the base system, SI system of units, so that one does not make a mistake in the order of the calculations. Let's calculate alpha 2 now. Alpha 2 is given, I'll write the formula again, just for the sake of completion. So you can very well see that before we start calculating the numbers and substituting, we do need the value of alpha 1, which we calculated in the previous slide. We do need the value of nu1 2, which is the in-plane Poisson's ratio, major Poisson's ratio, where nu1 2 is nu f VF plus nu m VM. And we have the Poisson's ratio of the fiber is given as 0.2. Volume fraction is 0.7. Poisson's ratio of the matrix is given as 0.3. Volume fraction is 0.3, and that gives us Poisson's ratio nu1 2, the major Poisson's ratio, as 0.23. So once that's the case, what we're going to do now is we're going to calculate alpha 2 just by substituting. Nu f is 0.2. Alpha f is given to us as 5 times 10 to the power minus 6. The volume fraction of the matrix is fiber is 0.7. And then we have 1 plus nu m, which is 0.3, thermal expansion coefficient of the matrix is given 63 times 10 to the power minus 6. Volume fraction of the matrix 0.3 minus alpha 1, which we found from the previous slide, which is given as this, and then multiply by nu1 2, which we just found out, which is 0.23. And if we do these calculations, we get the value of alpha 2 to be 27.40 times 10 to the power minus 6 meter per meter degree Celsius. So we have found alpha 1 and alpha 2. One of the things to observe, although this is not part of the example, is to see that how alpha 2 and alpha 1 are varying as a function of fiber volume fraction. So we calculated for 0.7, so these are the numbers which we calculated in our example here. But look at how alpha 1 varies. It goes down like this. However, look at this alpha 2. Alpha 2 is not in between the values of alpha m and alpha f. The value alpha 1 is, of course, between the value of the thermal expansion of the fiber and the matrix, but not for alpha 2. Alpha 2 is turning out to be greater than alpha m at this, for this particular fiber volume fraction. It is the maximum which you get. In fact, you can calculate what is the combination of the fiber and matrix properties which makes the alpha 2 to turn out to be greater than alpha m for some fiber volume fraction. But that's a different example. But one thing which we need to appreciate is the fact that, hey, the alpha 2 is also not bounded by alpha f and alpha m in most polymer matrix composites. And that's the end of this segment.